Hi again, everyone. This lecture is part B for chapter 17 and 33 module. In this lecture, we're going to cover section 17.3. So let me go ahead and share my screen for that. Um, so you can see that this lecture is going to talk about interference. It's going to be hopefully relatively short compared to the previous one. And I'm going to break these lectures up into the kind of corresponding to the different sections. So let's talk about interference. We've talked about this before with regard to chapter 16. When you add two waves together, you can either get constructive or destructive. So hopefully you remember that constructive interference is when the waves are kind of in phase and they add up to a maximum amplitude. Destructive interference is when they're out of phase and they cancel each other out and lead to basically zero or very close to zero amplitude. So in this section, it's exactly similar, right? If you remember from chapter 16, we added two waves together. Now we're going to add two sound waves together, but it works out very similar to what happened in chapter 16. In this case, let's consider a wave S1 here that's got an amplitude SM, so we're talking about the displacement in this case. And then I've got a cosine of kx minus omega t. Now, we're going to add a second wave, S2, that is just out of phase by an angle phi. So this is our phase difference. Now, the phase difference could be caused by various things. It could be caused by starting the sound at a different time. As we'll see in this section, it often can happen due to what we call a path length difference, in which the waves have traveled a different distance before they overlap and add to one another. But let's look at the mathematics here. If you add these waves together, and if you remember from chapter 16, again, we used a trig identity to do this, but it works out exactly the same. The result is that we get an amplitude part, this 2 SM cosine 1/2 of the phase difference, times a traveling wave part, right? So it's still basically a traveling wave with the same wave speed, but the biggest difference is that we've got this amplitude that's modulated by the phase difference. So we get a new amplitude, and this amplitude is going to depend on phi. And as you can guess, this is where we're going to get our constructive and destructive interference from. So let's look at that amplitude and the phase difference and see how it does relate to the constructive and destructive cases. So if you look at that, if phi is a multiple of 2 pi, right? So say 2 pi times m, where m is 0 or an integer, you'll see plugging it in to this formula here, I'm just writing the formula again for s prime m, I'll see that the cosine of 2 pi m over 2 is equal to 1, and s prime m is double the individual amplitude of each wave. So this is, again, constructive interference. So if I have a phase difference that's a multiple of 2 pi, or actually 0, right? If phi is 0, I'll still get constructive interference. But any multiple of 2 pi will lead to constructive adding interference waves. Now, it makes sense because if I go by a cycle of 2 pi, I'm just kind of back to where I started. If you think of a circular situation, right? I'm just repeating. And so if I shift one wave by 2 pi, I've really just shifted it back to the same wave. And so I'm adding two exactly the same waves together. Now, in the case of the destructive interference, what I could do is I could say, well, let's say phi is an odd multiple of pi. So it's either pi or 3 pi or 5 pi. Another way of writing that is to say it's 2m plus 1 times pi, where m is, again, 0 or 1 or 2 or 3 and so on. So m is a 0 or an integer. But now you'll see that when m is equal to 0, I just get cosine of pi, and that's equal to 0. Cosine of 3 pi when m is equal to 1 is also 0. So anytime I've shifted by an odd multiple of pi, I get a resulting amplitude of 0. And that's our destructive interference case. So the waves have canceled out in that case. And again, it makes sense because I have only shifted by pi, which is 180 degrees. I'm kind of going the opposite direction, right? I'm going backwards now. And when I add those two waves together, they cancel one another by destructive interference. Okay, so now let's talk about the path length, because often what happens, and this is important as we'll see later on for light, that if you have two sources of sound like S1 or S2 in this picture here, and then maybe these are speakers, right? And I'm standing over at this point P. When the sound waves reach point P, they have traveled different lengths, different distances, L1 and L2. Now, if L1 were equal to L2, they would just be the exact same, and I would get constructive interference. But if L1 and L2 are different, I get what is called a path length difference. Let's call it delta L. It's L2 minus L1. That's our path length difference. And you can see that if the difference is equal to, say, for example, twice the wavelength, well, then the waves arrive again exactly in phase, right? I've just shifted by 2 times, and I'm back again to where I started. And so I get constructive interference. They're just kind of adding together. Now, if I shift by a multiple of half the wavelength, say 2.5 wavelength, like in this picture, well, now I'm back to that odd multiple of pi situation, and I'm going to get destructive interference. All right, so again, the rule is that if I'm shifting by a wavelength or a multiple of the wavelength, I'm going to get constructive interference, right? So that's that statement here that delta L is a multiple of lambda, it's constructive. But if I shift by a multiple of half the wavelength, I get destructive. So what this ultimately leads to is I can relate this delta L path length difference to the phase difference. And the way I can look at it is that, if phi is my phase difference and I divide it by 2 pi, it's kind of like taking what fraction of the full circle am I making? Well, that should equal the phase or the path length difference, delta L, divided by a wavelength, because one wavelength corresponds to going through an angle of 2 pi, right? As far as the cosine and sine functions go, I'm just repeating after 2 pi or one wavelength. So this relationship holds, and then you can see that for constructive interference, right, phi is 2 pi times m, so delta L is a multiple m of the wavelength. Now m can be 0 here, and that again means that there's no path length difference, they're just the exact same wave. But anytime this condition is satisfied, delta L equals m lambda, I get constructive interference. I get the waves adding together. On the other hand, if phi is a 2m plus 1 times pi, it's an odd multiple of pi, well then delta L is equal to m plus 1/2 times lambda. You can plug that in and derive this. And again, I can use m equals 0, 1, or 2. It's an integer or 0. So if m is 0, I get delta L is a half of a wavelength, and I'm in my destructive interference situation. So again, these formulas are going to be important. In any case, you have a path length difference. Whoops. If you want to determine whether there's constructive or destructive. Now you might ask, well, what happens if it's not a multiple of the wave, not an exact integer multiple of the wavelength? What if it was 0.8 lambda? Well, then it's not quite totally destructive or constructive, right? It's an intermediate situation. The closer I get to an integer, the closer it's going to get to either constructive or destructive. So let's say I was like 0.9 lambda here, and I'm close to a multiple of the wavelength. Well, I'm going to get a large wave, but it's not going to be the total maximum amplitude of 2 SM because I'm not quite at that condition. But you'll be close, right? And so what we're going to end up using are these conditions here to determine, for example, whether we've got constructive or destructive interference. And we will see this more when we talk about interference for light waves after we get past chapter 33. So as a last thing here, let me just do a quick example. This is, again, a problem from the book. And what this problem is asking is you've got two sound waves, A and B. So A and B they're both traveling to the right, and then they hit these reflecting surfaces. Now this would be very similar to what would happen for a light wave or an electromagnetic wave, and these were mirrors, right? So I've got sound wave A reflecting, hitting here, reflecting again, and then finally having a third reflection. The question is, well, first of all, actually, B goes only through one reflection. And it says, let the distance L be a multiple of lambda. L is equal to Q lambda. What are the smallest and second smallest values of Q that put A and B exactly out of phase with each other? So when they say out of phase, what they're asking for is destructive interference. And I know from the previous slide here that delta L is going to equal a multiple of half the wavelength for destructive interference. What we need to determine is what is that delta L? What is the path length difference between A and B? Now let's look at this. So if I look at A, I go through the same distance as B until I hit the first mirror. And then what happens is I go through 1L, 2L, and 3L, and then I'm out. Right, so I've gone through 3L in my reflections. Now let's look at B. I'm going to hit here and I'm going to go 1L and then 2L, and then I'm out and I'm back to the same point that sound wave A is. So what is my delta L? Well, delta L is 3L minus 2L. Does that make sense? So I've gone through 3L and 2L, and really the difference in distance that the waves have traveled is that A has gone through this extra length L right here. That's the only difference in the path that the two waves have covered. So it's equal to L, but we know from the problem that that's equal to Q lambda. So what I get is that Q lambda has to equal M plus 1/2 lambda if I'm going to get destructive interference, if I'm going to be out of phase. Now, the smallest case, the smallest value of Q would occur when M is equal 0. And so if M is 0, I get Q, the lambdas cancel. Q is equal to just 1/2. So L would be half the wavelength. The next smallest is going to occur when M is equal to 1. Right, and that's because now I'm going up to not 1/2 lambda, but 3/2 lambda. All right, I'm adding another odd multiple of lambda, but I still am out of phase and I still get destructive interference in that situation. And this would correspond to Q equals 3/2 lambda. Or sorry, actually, you don't need the lambdas here, right? It's just 3/2 and 1/2, because it's telling me that that's the multiple of lambda that I need. So this is the answer for A, and this is the answer for B. So you'll see in the homework a problem where I actually is kind of more like the picture I showed in the previous slide here, where I've got 2 point sources, and you got to calculate L1 minus L2. But it's very similar. The idea is that delta L path length difference has to equal a multiple of the wavelength to give you constructive interference, or a half multiple of the wavelength to give you destructive. And again, we will see this once more when we talk about interference of light.